Yeah.
Right.
Yeah. So Kai was my PhD supervisor. I was your first PhD student, and what I think is really amazing about Kai is that when you look at all the amazing PhDs he produced, he didn't quit after me. So yeah, Kai's done a whole lot of incredible things. Pretty much any area of systems. He founded Data Domain, and with all the huge amounts of data we have in the world, you don't want to lose it. And Kai's, of course, made huge contributions there. I'm sure anybody who's done computer vision has come across ImageNet, which is Kai's work. He's now working on language models and privacy issues with that sort of. It's like anything you can think about systems, Kai has done. It's absolutely amazing. And beyond that, he founded the Asian American Student Foundation, or
Scholar
Foundation, and has been working on causes of transparency and equality and fairness, and seeing the societal implications of the technology that we do and how we pursue it. So with that, it is an incredible honor to have you here at UBC today.
Thank you. Mark, thank you for the kind introduction. But I would just say a few words. First of all, it's here to give a distinct. The Mark. And he's one of the individuals who just did his thesis, without help by there. So that's amazing. That to see him. Also, it's a great opportunity to see my old friend Joe Freeman, who is always in my memory. Like we hang out for multiple years as together as assistant professors, and my memory is like Joe is one of the smartest people I ever known. If I have any question, I don't understand, he's my private consultant. And I see my old friend Margot. Every time I open some proceedings, she's Unix. I thought it reminds me Margot, who made things open, public, and besides her great contribution in system research, and she cared about the community and cared about people. And I also see Xiaoxiao, who is my recent postdoc, and she was telling me she's teaching 3 courses that have 9 students. I mean, this is amazing, capacity to help the community. So, and also I met many faculty members who are doing wonderful research, especially young faculty members who are doing things exciting. And I think in this era of AI era, I think they're working on something that have a lot of potential to make a high long-term impact. So back to the lecture, I'm thinking the way I've been working on things is always from the perspective, I think it's similar to many system researchers here, from the angle of how can I build a deployable system as opposed to just publish a paper, right? And that has a different level of complexity. And so today's talk is an example of students and a collaborative team working along that line to try to solve the problem of caching, which has been studied in decades. So first, I listed several collaborators. I believe Daniel Berger said he actually recently visited here. So some of the information we talk about, he probably already shared with people. And let me just go, how do I advance this? Maybe something, So first thing I want to mention is that machine learning is not only transforming the community, but also in particular has been transforming how we design systems. And there are several examples I won't mention, but is able to solve problems that in many areas that people have been working in multiple decades, and using heuristic algorithm and machine learning coming in, and we'll be able to show they can do better. And in some cases, better than human experts, right? And we're interested in the caching problem in this presentation because cache exists everywhere. We all have processors that have hardware caches, and in every OS and storage system, we have caches, right? And because that's a way to use a smaller, expensive storage at the higher level storage, and to hide the slow storage to improve the performance, to deliver high performance of the whole system, lower cost. And also things like content distribution network, where that delivers about 70% traffic, somebody have reported. And that all going through the content distribution edge caches, right? To avoid fetching objects from over the wide area network from the source. And the other thing I want to just briefly mention, so we're all on the same page, is that the way we're working on cache over the decades is we want to minimize miss ratio or improve the hit ratio. And but also there's another measure called the byte miss ratio. The miss ratio for objects miss ratio typically means that you fetch object in the fast storage. If it's not in there, you have a miss. Then you go to a lower storage, and that you measure how many of them you miss over the total number of accesses. That's a miss ratio, object miss ratio. But for content distribution network, we're talking about different measure called byte miss, because object size vary, and what you want is to minimize the traffic over the wide area network to fetch information. So you want to measure how many bytes you reduce. So total number of bytes, missed bytes over the total number of requested bytes. That's a little different from the traditional hardware cache and other cache design criteria. So in this talk, we're working on focusing on content distribution network cache. So we're following the byte miss ratio measure. And the other background information, a lot of people working on cache would know that if the object sizes are equal, then the offline optimal algorithm was proposed by Belady, or Belady means algorithm back in the 60s, right? Belady mean basically says that we want to evict object whose next access is the furthest in the future. And in this case, you use a time to next access as a measure, then you want to evict object with a maximum TTA, right? And there over 50 years of work, mostly working on heuristic algorithms. Then those kind of algorithms have been used in various systems. But if we look at different algorithm common for content distribution network, and you over a particular trace here, particular workload, let's say I'll use a Wikipedia trace, then you see that there's this large gap between the offline optimal and the top state-of-art heuristic algorithms. And this is partially because heuristic algorithms work well for certain access patterns, but not work well for other access patterns. And this gives the opportunity for machine learning to bridge this gap. Even after 5 decades, the gap's still pretty large. And then the question is, can machine learning come in to bridge that gap? Because machine learning potentially give the opportunity to adapt to different access patterns if you can do training and learning online, right? So that's the question we're asking. Can machine learning help design a better practical cache systems that we can deploy? So to answer that question, we can look at the generic machine learning-based cache architecture and to see what kind of questions we want to answer. So in this architecture diagram, we show the path access, access stream. There's some path request and there's a current request. The current request go to the cache, and you want to know whether things are in the cache. If it's not in the cache, you fetch, but you not only you fetch, but you put new information in. You have to evict some object to make room for the new object, right? Then you need to figure out who to evict. If you do machine learning, you also need training data to train your model, and the machine learning model will recommend which one to evict. I mean, that's essentially the high-level thinking, high-level architecture, right? So there are several questions we want to ask. One is that you have some past information. We want to, machine learning is fundamentally using past information to predict the future. Then what past information to use? How much past information you want to use? That's one of the questions we have to answer in order to design a system, right? If you have more information you want to use, then you need to have a lot of place to store the information, right? And that's not good if you want to deploy practical system, because you have more space to store, you have less space to store your data. So you're competing with that space, right? And also, once you figure out how much information to use, and we have to figure out how to generate training data to train machine learning model. And we want to be able to train online, their continuous training. Therefore, you don't want to have a lot of training data that would take forever to train. And then we also have the question, which machine learning model we want to use, right? Is a deep learning machine learning model or something else? And again, if the training model, if the machine learning model is very sophisticated, it may take like large models. We're talking about very large model these days. But in system, we want very small models because we don't want that to compete with the space we have to store cache data. Then also, if we want to make an eviction, we want to give eviction, right? How to select eviction candidates would be a question. So now I list the 4 questions we have to answer. And there's one more question. How would you evaluate design decisions? But in systems, where even machine learning, where you have to tune hyperparameters, in systems, each of the questions I want to answer, I have multiple design decisions, right? And the typical way people design cache, especially a content distribution network kind of cache, is that you experimentally evaluate your design decisions. You collect a bunch of realistic workload. Like in content distribution network, you have traces from content distribution network companies. And maybe each collected over 5 weeks, 2 months, some large amount of time. And then you run them over the simulator you built with your algorithm. And then you say, which one give me the minimal byte miss ratio, the metric I just mentioned. Well, that would take days. If we have 6 traces of each is multiple weeks. And in our experience, it would take days to get the answer back. So then you say, okay, this is not good. I will come up with a different design decision to answer one of those questions, where I modify multiple of them, I try again. This iteration takes too long, right? So then the question is, can we do something faster to evaluate so that we can try different design decisions? So that's one of the challenges. So going back to the Belady algorithm, which is considered optimal, but even though when object sizes are not equal, it's not really optimal, but it's close to optimal. Let's just consider that. This Belady algorithm that Belady mean is nice because it's talking about evicting object whose next access is furthest in the future. Well, TTA is the maximum. So then, but we don't really know where the next access is, where they are, and machine learning may be able to do prediction where the next accesses are, and maybe we just use that to mimic this algorithm, right? And maybe we'll have a good results. But there are some challenges if you mimic this approach. I'll just list challenges. One is the workflows are very diverse and changing, and sometimes you predict well, sometimes you don't predict well. And also, when you predict something next access which is far away, that's typically more difficult than you predicting something close by, right? And the next access is close by somehow is indicating that, implying that your accesses are quite frequent. So you'll probably do a better prediction. And so that's one of the challenges. And if we're talking about finding the maximum TTA of all the cache objects, the number of cache objects in the cache could be millions. Can we compare all of them to come up with something the furthest in future? That wouldn't be practical, right? So that's a challenge. And also, I already mentioned machine learning competes for memory space for cache data. So one key observation, we were able to make progress. I'll just have to admit that we worked on this for like over a year. We didn't make progress. We talked to some friends who are working on this in other system group. They couldn't make much progress either. But there's some time all of a sudden we have an observation. I'm just going to report the observation that let us make progress. That's what we call relaxed Belady mean algorithm. The concept is quite simple, but once you're able to come up with this observation, you'll be able to, we are able to make a lot of progress. And this observation is to establish a boundary in the dimension of time. And this is pretty far out. So basically anything above the boundary, of the boundary, we'll consider them same. If the next access is 1 year, it would be about the same as 2 years, right? So we're just don't care. We don't care about distinguish them. So by doing this, we can simplify the machine learning problem to be binary classification. It's like I just need to consider, is that on the left-hand side of the boundary or the right-hand side of the boundary, right? And then if when I make decision to select who to evict, anything above the boundary, I just select them randomly. I treat them the same. So that would make life simple. So one other problem challenge this observation solve is to be able to, now we can use random sampling to select eviction candidates. You know, for example, if this boundary is on this side is maybe 90%, side is 10%, then you sample enough, you know, you will have you don't have to sample so much to guarantee that you have candidates on the right-hand side of the boundary with high probability, right? So then this will become practical, right? So in this case, we experimentally select where's the sweet spot. And I think in the prototype system we built, it was 64. So you can sample 64 objects, you run 64 inferences, which simple machine learning model you can run fairly fast. Then you compare, you know, you figured out which one on the right-hand side of the boundary, and then you decide your eviction candidate. So with this observation, it also solved another issue, which is what we for the evaluation cycle problem. So we call this concept good decision ratio measure. So we're using the relaxed Belady algorithm to help us forming this kind of a scenario where using good decision ratio as a way to select design decisions. And then now we can reduce that iteration to minutes. Then we can adjust the design decision to address the other 4 challenges very quickly. And let's say, so if it's on the left-hand side, you make the eviction decision with that considered bad decision. And you consider good decision. A good decision rate is the number of good total eviction decision. And using this to collect this information, you can collect during a relatively short time period. And then you can iterate, right? You don't have to wait until to see end-to-end results. So now, with this in mind, we're trying to figure out how we did solve the problem for each of the challenges, right? So first is that what past information to use. And obviously more data will improve training, but what we did is that we will, when we have a Belady boundary, we basically says that we only keep the use that to help us define how much past information we need. If the Belady boundary covers the established at 90%, then you only need to keep, a window of information in the past that can help you do this kind of prediction. So that's the typically maybe 10 times size of the cache in that case. So then it's not that much information. If you add them all together, it's about below 1% of the total memory footprint. So I would just say it becomes a sliding window that mimics the Belady boundary. And then each of them will have a per object feature. So using typical information, the system, when you build system you have. And this is a hyperparameter we experimented, right? And then I will report the specific results later. The next one is how to generate training data from that window, right? And the way we did that is that we'll sample training data and label on each axis or Belady boundary. And then we sample the data, some of them are unlabeled training data. Then when you access, the access will label the training data. And then, obviously this is from the memory window, and we use that to train data. That typically, the amount of training data is about 100, we were using 128K. That's a very small number, so we can train in sub-second. We can train each time we train. So the model get updated at that frequency. And the next is what machine learning model we should be using, right? So we did some evaluation, and it turns out that and using decision trees, because that's very small, and we with various machine learning models. As good as and the issue is how to select eviction candidate. So I mentioned earlier where we're randomly sample, and So if we mimic relaxed Belady, we just need to have one object young boundary, right? And then currently we if you put everything together, it looks like this, right? The first sample unlabeled data from the past information, and then you label them, and you train the boosting tree model, and then boosting tree model, then we sample eviction candidates, and then model prediction, and give the prediction recommendation or decision to the cache, and the cache makes that decision. This is how what the workflow is. So we did the implementation of a simulator, and so to compare with other approaches, we compare with 14 different algorithms. We also built a prototype with the Apache track server to see how the real prototype would work. And the evaluation, we try to answer the question, would this approach we call learning relaxed Belady IRB, does that reduce how much does that reduce the traffic compared with state of art? And the other is the overhead practical, low enough to be practical comparing with by building a prototype. And also we have 8 production traces from 4 different CDN companies. And then we tune the parameter, and we have a warm up with about 20% of trees. So this is the workload we have. Here actually just shows 6. Maybe in the paper we won't have 6. So I would just because of the time, I would just skip the trees description, and using Wikipedia trees as example, the industry standard in the content distribution network is they typically use called the ARU, least recently used algorithm, but with a Bloom filter in front to filter out what's so-called one-hit wonders, which is you only access once, you never access again, you use the Bloom filter to filter them out. And that's typically what a lot of companies are using. So we're comparing with that, vary the size. And what you see is typically this kind of figure. The dashed line shows the BLRU, that's the kind of standard. And traffic reduction, higher the better. Some of the algorithm actually does better than BLRU, but the LRB, which was just substantially higher traffic reduction than the rest. And this you can show that with other traces. I'll just show you all 6. And the blue line is what LRB achieves. So that's better than all of them with different cache sizes. So then you build up, if you show the prototype results, you also show you can indeed do better. But also the overhead is quite small. The throughput is about the same compared with without using RB, and the overhead is minimal. So the takeaway, I think, for this part is that our experience is that using machine learning to do better system design is actually difficult. And the key to solve this problem is to figure out how to frame the system design problem as a machine learning problem. So this part, as long as you figure out how to frame that, then you can make better progress. And that's a lessons learned. And here, the key idea is to relax the Belady min algorithm. And that observation let us make a lot of progress. Before we were able to frame the problem this way, we couldn't make progress, right? And this is simplified the machine learning problem, but also allow practical implementations. And the good design decision ratio is a good metric to allow us to iterate our design rapidly. And the weaknesses of this approach, you still need, in this case, k inferences per eviction, where k is equal to 64. And for certain other design, cache design, this could be still significant overhead, right? Because for a content distribution network, object sizes are quite large. If you deal with a cache because the object sizes are smaller, then we need to work on this part. So that lead us to the next piece of work. That's we call machine learning at tail. And the question trying to solve is, can we substantially reduce that 64 inferences per eviction? And one main application is that heuristic algorithm is such. So the reason is that if you find by the minimal distance of all Belady eviction decisions, let's say if you use that as that line B, right? And you on the eviction decisions that you may not, but you B, and you will see that error B, error U, I mean error U, that error U, probable error is going to the right, and the other half is on the left side. Well, what this means is that, and also if you look at the right-hand side, the bar height is similar to the Belady algorithm, right? The optimal algorithm, meaning that most of the decisions that Belady is making, LRU also make them, but it just make more mistakes. Half of them would be the objects you don't want to evict, and LRU tell you to evict, but only half of them. So this has several implications. One is if you use LRU as a, I can filter out most of the unnecessary decisions, right? On average, 1 out of 2 would be good enough. If you build a system well, then you only need to run 2 inferences on average to make a good eviction decision, not 64, but 2. And 2 will be minimal because you can't just do 1, you have no comparison, right? So that's pretty exciting if you can reduce to 2. And can we do that? Okay, I already said them. And then before going there, let's look at the other kind of a heuristic algorithm, such as FIFO, first in, first out, LIFO DA, and that's least frequency, LRUK, and so on, and comparatively to what happened. So what you see is that the LRU will make the different eviction percent, right? 4%. So as a future, that's good. If you have FIFO, is also reasonably good, to our surprise. Maybe one of them is 87%. But FUDA, some of them better than LRU, and one of them is not as good. LRUK, almost all of them are better, but maybe one of them is not as good. Of course, Belady is 100% because that's how we do this problem. And the other, you want to positions, right? LRU essentially give about half, on average, maybe a little less than half. FIFO, it's similar, maybe a little more. LFUDA, less than error U, and error UK, some of them are a lot more, right? And Belady is obviously 0 in that case. So this kind of a figure sort of shows us heuristic algorithm, many of them could be served as the filters. And they can make the system can substantially reduce the number of inferences you have to do. Now the question, how would you, with this information, how would you design a system? So then we're thinking, what you do is that you have the traditional heuristic algorithm. Let's say we have priority queue, and then you have the machine learning component, which has training data set, eviction candidates, and you have the model. What you do is you link the tail of that priority queue to eviction candidates, right? Out to that model. And then if the model says, yes, this is a good one to evict, it's on the right-hand side of the boundary, then evict it. If it's on the left-hand side of the boundary, let's reinsert. We provide an API, reinsert back to the priority queue to the front of the priority queue. And that's a very simple operation, right? Anybody doing implementation will be able to tell. Okay, this will be a simple hook to the future. This is how we do this. And the training data will be accumulated by the eviction candidates. So we use the eviction candidates information to train the machine learning model. Would this even work? So we build this up. Just like I said, I think this is just for elaborate algorithm method. This set. I'm not going to repeat that because of the time. Then we build a simulator and also a real prototype to see whether this really works, right? And we're interested in the number of predictions per eviction we need, and the choice of a heuristic algorithm, and measure the prototype performance. So you see that, again, here we have 7 different workloads, a little different from the other ones. But so this object sizes, average object size vary from 2 megabytes to 400K, about 300 bytes, and so on. And we want to see how they behave, right? And we build a simulator using the Facebook or Meta CacheLib library, and we build a prototype out of that. Also, again, we compare with the 14 algorithms we talked about before, as well as LRB, the previous approach. Then you look at here, this actually shows that doing 2 predictions would be as good as more. So that's exciting, right? We can reduce all of a sudden from 64 to 2. Then we can do many exciting stuff when dealing with a small objects in the cache, and all that stuff would happen. And we also saw that it's sensitive to choice as a filter, because if you look at this LRU, 2Q, tiny you compare with the 3, you see that if you use a machine learning LRU, a machine learning 2Q, and machine learning tiny, they're kind of all clustered together at the bottom. This means that the byte miss ratio, they're all similar when you vary the heuristic algorithm as a filter, right? So that's exciting. So if your existing implementation has some kind of heuristic algorithm, it's very likely you hook up the way we recommend, you'll be able to build a system that machine learning help you make better decisions, improve your cache, right? Then you don't have to touch the rest of your software stack. So that's kind of interesting. And can we reduce the software overhead substantially? The answer is yes. Essentially, you reduced the number of prediction by 32 times, right? Naturally, and the number of training samples substantially reduced by, on the order of magnitude. I'm so sorry. Time, the number of training example, because now we only use eviction candidates from the heuristic at the tail to do training. And the prototype performance that's similar. Power. I just want to pause a little bit the questions before I talk about real deployment. Any questions? If not, I'll go on and answer more questions later. Okay. I think that if you build systems, I think one of the question, I'm sorry, the Zoom seemed to be in the way. And you want to come from the deployment perspective. Can we deploy a learned CDN caching system based on what just talked about with all this information I give you? And well, the reason I'm asking this question is the answer must be yes, right? So, so how can you do that if it's deployable? So our student who led the era did the intern at YouTube, and the reason why get him is because they saw the interesting results from the era B system. Then they said, oh, maybe you can try on our workload internally. And they try, oh, it's really better than what we have. Maybe we should try to implement that. And then they work on their software environment and build what you call the heuristic aided learn preference. You have to come up with something that YouTubers like, right? And that's what they have help. And then later, after months of effort, and they were able to deploy. So today, if you're using YouTube, your traffic is deployed by the system. So that's a pretty exciting. And they also just published a paper at SDI this year, so you can check out. So let me just give you a high-level overview of how this is done, right? So basically, their view is that heuristic algorithm is over there, the bad miss ratio is relatively high, and the SOTA learning algorithm is over there, that's like ARB. But what they want is to build something, add a little bit of computational overhead, but have a similar byte-miss ratio as the learn algorithm that does pretty sophisticated stuff. And they just add the heuristic plus, like I mentioned, like the MAT approach. But what the difference is that they're looking at more things at the tail, not just two of them. Even though we show two of them, the company people have different ideas, right? So, and they did their own measurement. They showed that you reduce byte-miss ratio by about 9%. And you can find more information from that paper. And also has the best, with the simulation results, it has the best byte-miss ratio over CPU overhead combination, over state of art. So you show this, the green curve is adapted to LFIU. That's probably the best for their workload, and the help blue, and the dimension is normalized by mesh ratio. So they actually have substantial reduction. And this is why they were convinced to deploy. And ARB is essentially overlap with that. They run the simulation with that too. It's very similar. And ARB with a more straightforward for eviction is not as good. Okay, so that's the three parts, right? Machine learning using relaxed Belady algorithm. We mimic that using machine learning, and we have an effort to reduce the number of evictions for practical purposes. Then we made the effort to implement, deploy the system. So the lessons, again, it like we can build a practical cache than the state-of-art heuristics, right? And again, framing the caching problem as machine learning problem is critical. And mimic relaxed the mean works well. That works well in simulation, works well in prototype, works well in the deployment system. And heuristic can be effective filters so that we can make the system practical. And there are also still future work, like we haven't really tested for other different kind of caching environments, whether more sophisticated models will do well. I mean, this is like now we're in the era of pre-trained models, fine-tuning models. Would that be a good paradigm for this? Then we can substantially reduce the warm-up time if that could work, right? And then can we work on even much smaller objects? So those are the kind of things that I think is still open. So with that, I just want to add my talk, and thank you for listening, and please ask some questions. Thank you. Margot. Hmm? I don't believe so. There is another hand, yeah. Yeah, very good question. I think that in our case, it's really, we just did that experimentally. I think there are some previous work in hardware showing that for hardware cache, if even though what they're trying to do is mimic machine learning. I mean, this is we're talking about the work from University of Texas, Austin, right? And they said, well, typically you need to have past data maybe 8 times of the cache size. You need a metadata that size. That kind of imply your Belady boundary is about it implies where the Belady boundary is. In our case, our experiments shows that it's somewhere between 10 and 20 would be the past information. That means the Belady boundary would be 90% or 95% in the timeline. Yeah. Again, this is the kind of experiment that get help with a good decision ratio so you can iterate quickly. Yeah. So we experimentally do that. There's no theoretical results to show how to select that yet. So it'd be interesting to see whether any analytical work could be helpful. Mark.
happening in the future, right?
Right.
That's what you should add to that.
Right. Yes, that's a great thing. And one of the students actually looking at this prefetching in this framework for this, but also we did some previous work. Another student did a at Facebook using their workload, predicting the popular videos, YouTube videos. Like they want to predict the top 1% of the popular videos online. So we did that successfully. So that kind of knowledge can help prefetching, right? It's essentially similar. So I think the answer is yes. Yeah. Great thinking. Yeah. Yes. Right. Yeah, I think a hardware cache has a lot of constraints, right? Because, L1, L2, L3 caches, you probably have to work on the lower level cache, and but you still have a lot of constraint. Every bit you add counts, but it's not like so that's a challenge. I think people in computer architecture community, like what I mentioned, the Kelvin Lin's group at University of Texas, Austin has made some good progress. And that's, they did not use sophisticated methods. They do, very aggressive approximation in order to design something that could do for their simulation. I think between hardware and the content distribution network, there's a wide range of caches, right? With a different size of objects, right? And I think that's what I talk about in the future work, that whether we can build efficient learned cache with a very small objects. I mean, the work we did that could reduce the number of inference to 2 on average, it is a good effort towards that angle, right? But whether you're going to encounter other issues, that's still remain open. Any other? Yes. Oh, using heuristic algorithm, what's the maximum? Yeah, the maximum is roughly 10. Yeah, but that doesn't happen very often. Therefore, overall average is 2. That's what we found. It's kind of a not so intuitive, but somewhat intuitive. Like if your Belady boundary is set at the 90% point, if you get 10 of them, you probably have 1 of them on the right-hand side of the Belady. When you have a future, it's no longer the case, but the worst case may be like that. Then you still have 1 on the right-hand side, the Belady boundary. Yes. And we thought that the machine learning has to do that multi-level fashion, but just 1. Yes. Good. Good question, and good that it's good thinking. I think that when you have multiple level caches, if you look at the content distribution network, typically you have 3 level caches, right? RAM, flash memory, and the disk, right? Why disk is a cache? Because this is caching over the wire network, right? And so, so then the question is that which level cache should use which algorithm? This is still open question. So we're focusing on the memory level because that's where give you the performance throughput. Yeah. Yes.
Focus on the centralized caching, or also consider the distributed caching.
Right. That's a different setup. So our experiments only use the edge cache traffic workload to evaluate. So you would need to use different workload to justify experimentally whether that will work. But my intuition is it would work. Yeah. Yes, Steve.
Discard items that have come before.
Good. So because so Steve is asking whether we use Bloom filter to discard the one-hit wonder objects that only access once. Well, we tried to put a Bloom filter in front, ARB, and try to do without our Bloom filter. It turns out we don't need Bloom filter because the kind of learning algorithm somehow take care of that. Interesting. So experimental answer, right? It's not, we don't have the analysis for to show that must be true. But again, more analytic analysis could be helpful, assuming access follows certain distribution. You may be able to get some interesting results to show. But we did an experimental study to show it's not necessary. Yes.
Static, some static features and counters. So I'm assuming there must be some features that I wanted to know what was the thought of the selecting. Was it just empirical evidence, or was there more?
Right. Clearly, you have read paper carefully. I thought I could get away without talking about that. So what happened is that we don't have a lot of features. I mean, that's the thing. We have information like object size. We have then you have when the access happened, right, in the past, right? And that kind of information is kind of really simple information. And our work previously for the video popularity prediction, we actually learned from that project that you need to keep enough history information to do better. But the history information is kind of weird because if you talk about the past, when the access happened, you kind of have either relative or not relative timelines, right? And you have delta kind of information. And it turns out that as you move forward, that information is changing. So all that delta stuff that decayed over time, we're using log, is to deal with that problem. It turns out that approach, more explanation is actually in the video prediction paper and could be helpful. Then, experimentally, it turns out to be true. That's actually quite important. And this is why I didn't want to deal with that problem, because that's in the mud. Yes.
And eventually making machine learning not feasible. So it has to.
That's an interesting thinking, but the way we update is like every a few seconds we update the model, because our training time is only 300 milliseconds. So the goal is to be able to adapt to current access patterns, not using the model trained, using long ago, much further away past information. But this is why I listed more sophisticated models that would include the kind of question you're asking that deserve some more investigations. You know, even you're using the small boosting tree model, as we talk about, there are other issues like what you mentioned deserve some investigations. Yeah. Yes.
So the deltas are like when you find it timestamp probably down to second.
Yeah.
But what if the timestamp were not that binding? Let's say
Yeah, it turns out to be that's not as important because when you predict something far away, you don't really need that precise information, right? And we do have trees for especially for the second study I mentioned that has Microsoft storage trees and so on that didn't have that kind of a timestamp. Yeah.
More questions? Oh,
Yeah.
Things like heuristic audiences in an active system. What would be the impact of lower associativity? And you could say that
Well, you're talking about the hardware cache. That's why you use a fully associative. You know, we did not do such an investigation. In software, what you're looking at is fully set associative. But hardware, you have constraints, right? You can only build fully set associative caches of certain size, otherwise it will run slowly, right? And that kind of constraint, I think that's the kind of work hardware folks should be looking at. But our work doesn't address that question. Yeah.
Here, look, any other questions? Okay, well, let's thank our speaker one more time.